Okay, so in the last portion of our geometry unit here, we're going to talk about scaling. This really is coming from the second half of the book, chapter 9, MHH. A lot of the review is though also in here. So you're going to have problems for your homework at it. A little bit of scaling, but also a little bit of review from that chapter 9 and chapter 11 with transformations. Okay, so scaling transformations. A scaling transformation is a geometric transformation in which objects are either enlarged or shrunk while retaining their shapes. That is, we change the size of the objects, but the proportions remain the same. Okay. So we have some properties here of geometric properties of scaling properties. When a scaling transformation with scale factor A, okay, scale factor A, acts on geometric objects. 1. Every straight line is transformed into another straight line. 2. Angles are preserved. Okay, that is, the angle between the two intersecting lines does not change under scaling. 3. The length of any line segment is multiplied by that scale factor A. The length of any curve is multiplied by the scale factor A. 5. Areas are scaled by the square of the scaling factor. So the area of any region is multiplied by A squared. And 6, the last one, volumes are scaled by the cube of the scaling factor. So in other words, the volume of any solid is multiplied by A cubed. So these are important ones here. Not that the other ones are not, but ones you want to definitely remember here. Okay, so let's actually try to apply some of these to an example or two. So let's start with A. A sphere has volume of 1,000 feet cubed. What is the volume of a sphere with twice the radius? So this is telling you the scale factor. They're telling you that the scale factor is 2. So the new volume would be A cubed, because we're talking about volume, times the old volume. So again, the new volume, sorry, I should have spaced this out a little bit better. Should be, well, A is now 2, so it's going to be 2 cubed times, what's the old volume? 1,000. So that's 8 times 1,000, so that gives you 8,000 feet cubed. That's the volume of a sphere with twice the radius. Okay, so again, that's dealing with volume. A circle, for our next example, has area. So now we're switching gears here and we're talking about area. 500 square feet. What is the area of a circle with triple the radius? Again, this is telling you the scale factor is 3. So the new area is A squared times the old area. Well, A is 3, so 3 squared. The old area is 500. So that gives you 4,500 feet squared. And again, a good way to think about this, because area is always measured in squared feet. Volume is always measured in, well, doesn't have to be feet, but squared units. Volume is always measured in cubic units. Okay. So again, you always take the old times the scale factor cubed for volume, and you take the old times the scale factor squared for area. Okay, another example here. Radius of Jupiter is approximately 10 times that of Earth. So, part 1 here. How does the surface area of Jupiter compare to that of Earth? Well, again, this is really telling you your scale factor is 10. So if we're talking about area, right, this should be 10 squared. So that's going to give me and tell me that's 100 times bigger. And now it's talking about how does the volume of Jupiter compare to that of Earth. So again, we know A is 10. We're now referring to volume, so now we're talking about 10 cubed, so you're talking about 1,000 times bigger. Okay. Okay, so now let's talk about comparing surface area to the volume and talking about that ratio. So let's set this up. All living cells produce heat as a byproduct of their metabolic processes. The more cells, the more heat they generate. Thus, the greater the mass of the organism, the more heat it generates. To maintain thermal equilibrium, they must be able to get rid of excess heat. The heat is carried away by contact with a cooler medium such as air or water. The rate at which an organism can dissipate heat is proportional to its surface area. The rate at which an organism generates heat is proportional to its volume. Okay? So those are two important concepts that are going to relate surface area and volume together. So now we're going to look at the surface area to volume ratio. And how is this a ratio affected by scaling? This ratio describes how well an organism is able to get rid of excess heat. If the ratio is too small, the organism will not be able to get rid of enough heat. If the ratio is too large, the organism will not be able to maintain body temperature. So suppose an organism is scaled by a scaling factor of A. Okay? Surface area, just like we've kind of talked about before, the new one would be A squared, the scale factor squared times the old area. Volume, same thing, A cubed times the old volume. So now let's put that together as a ratio. So new surface area to new volume. Well, new surface area is going to be, again, the A squared, the scaling factor squared times the old area, over the volume. The new volume is A cubed times the old volume. Well, we can reduce this, so that's going to be 1 over A times the old surface area over the old volume. Okay, so this is an important little surface area to volume ratio. As the creature is scaled up, this ratio decreases it, making it harder for the organism to get rid of heat quickly enough. As the creature is scaled down, the ratio grows, making it harder to retain enough heat. Okay, so just another example here. In physical anthropology, there is a rule known as Bergmann's Law, which states that humans who live in cold climates tend to have thick torsos and short appendages, while humans who live in hot climates tend to have thin torsos and long limbs. The reason for this is that long limbs have more surface area and less volume, and so better give off excess heat. Likewise, thicker torsos have more volume to generate heat and less surface area to lose heat. All right, let's move along into stress here. When engineers design structures, one of the most important factors they must consider is stress. It's also an important factor in the evolution of living organisms. So in other words, larger animals require stronger bone structures to handle the stress imposed by their increased weight. With stress, this is worded a little awkwardly here. Let me kind of fix that. Stress is the concentration of force per unit of area. That is, it is the ratio of force to surface area. So total force over the cross-sectional surface area is what we're looking at there. For us, force is just the force of gravity measured by the weight of an object. The formula above shows the same weight exerts greater stress if concentrated on a smaller cross-sectional area. Also, for materials of constant density, the weight, or the force exerted, is proportional to the volume. D is the density of the material, then the force equals D times the volume. So the scaling law for stress is where you do the new force divided by the new area. Well, again, we're dealing with volume here for the force, so that's A cubed times the old force over the surface area, so divided by A squared times the old area. And again, these can reduce, so it's literally just A, the scale factor, times the old stress. Again, another important formula there. Scaling law for stress, so again, A times the old stress equals the new stress. So if an object is scaled by a factor A without any change in the density of materials, the stress is given by this equation here. Okay, so let's look at an example here. This simple rule explains why different materials must be used in constructing a skyscraper than are used when you construct a single family dwelling or house. So if we look at this movie here, we have a 1950s fiction movie, Attack of the 50-Foot Woman. A woman is exposed to radiation and grows to the height of 50 feet while maintaining the exact proportions of a normal human female. Okay, so let's answer 2 questions here. Suppose that prior to her radiation exposure and subsequent enlargement, she was 5 feet 5 inches tall and weighed 120 pounds. Also assume the materials in her body remain the same, bone material, etc. First, how was the surface area to volume ratio changed? And then the second question we'll answer is how has the stress on her bones changed? Okay, so let's first take a look at number 1 here. How has the surface area to volume ratio changed? Well, we actually need to talk about the scale factor. Okay, now I have the scale factor to be 9.23, but where is this coming from? Okay, so if we go back here, right? So we have, she was originally 5 feet 5 inches, weighs 120 pounds. But after the exposure, she is then 50 feet tall. Okay, so that is where this first portion is coming. So 50 feet divided by 5.416. Well, where is that coming from? Well, she was 5 feet 5 inches prior to the exposure. Well, I'm converting this all to feet. So 5 and 5/12 feet. Well, 5/12, if you plug that in your calculator, you're going to get that to be 5.4167. Okay, so the scale factor of after radiation divided by what she originally was is 9.23. Okay, so again, how has the surface area to volume ratio changed? So again, we're doing the area to volume of the new. So our scale factor is 1 over A. So if you remember your formula, it's 1 over A times the area over the volume of the old. So the scale factor of the old. So again, we don't really necessarily know that, but 0.108 when we do this division. So she's about can get about 11% of the previous rate, right? Getting rid of the heat. Okay, so the second question, how has the stress on her bones changed? Well, the stress on her bones is increased by a scale factor of 9.23. So again, if you remember, you just literally take the new stress equals A times the old stress. All right, so that right there is increased by that scale factor because that is A. So that is though at her original bones were supporting a weight of 1,107 pounds. So again, how do we getting that? Well, what we're really doing here is we're taking the for the weight, we're taking the 9.23, and she originally weighed 120 pounds, and that will give us 1,107 pounds. Okay. All right, and that wraps up our notes on scaling.